Okay, so here we are. Remember, we just integrated with respect to y and then x, and we figured out what our integral was. Now let's try the other way. So from 1 to 2, and then, oh my goodness, it's from 0 to pi. One to 2, x cosine xy d x dy. Okay, so we're working at this. We're going to work on the inside integral here. And you see you have two factors that have an x in it. So remember, we got, for this one, y is a constant. So that x is changing and the cosine of xy is changing. And now I would ask, do you remember how to integrate something like that? So if you have a product, what was a good go-to thing that we would have to do? And the basic gist is we'd have to go off to the side and do integration by parts. Okay, so just so you remember what the integration by parts is you gotta do u and then a dv and multiply those two things together to get what your integral is. So we're going to let u equal x, and then dv is cosine xy. And then you have to take the derivative of the left side of u, and then the integral of dv. Now, the derivative of x is not so bad, it's just dx. But then the integral of cosine xy is something different, so we have to go off to the side. And we can't integrate that right away. We should be official and put a dx on the end like you're supposed to. And so here, like we've been doing, you have to do a u substitution. Remember, u is the variable, so y is constant. And then do we have a y dx? We do not, so we need to put it off to the other side. Now we're ready to do the u substitution. And then we have 1 over y, which is our coefficient, and then we have du. We can find the antiderivative of that. It's just sine u plus c. And substituting back in for u is going to give you xy. Alright, so the antiderivative here for integration by parts is 1 over y sine xy. And then we don't have to worry about the plus c because we'll put that in at the end. Then, remember, integration by parts is you multiply u and v together, and then you subtract the integral of when you multiply v du together. So if we're going to be nice and official here and put it in, we can go from 0 to pi. We know what that integral is now. It is u times v, so it's x over y sine xy, and then we subtract the integral of 1 over y, which is a constant, so we can take it out, and then we have sine of xy dx. There we go, and then we still have to integrate the outside by y. So I just wanted to review what integration by parts was. But typically, if you run into that part, the integration by parts, perhaps you want to try this other way, the other ordering of y and x. And then see for this one, remember, we didn't need to use integration by parts at all. We just had to do u substitution a couple times. So we could continue on, and that could be a nice challenge if you're up for it, as you continue on. And you will be able to integrate this now. And you get -2 over pi. Okay, so keep that in mind. Sometimes the order will give you easier integrals to figure out. Okay, there's one less property that I wanted to talk about here with iterated integrals. We might run into the case where, so this is just notes for a property. Okay, so let's consider an iterated integral. So we're going to consider this one over r, and let's suppose we can put it into two different functions. So instead of having fxy and then dA, we can actually, the f of xy, we can change it to just g of x, so a function with respect to x, and then times another function with respect to y. And don't worry, we're going to do an example here in the future. The g of x is the only variable in there is x. There's no y's at all. And the h of y, the only variable is y. So we can rewrite this. Suppose we have r as that same rectangle. So we can switch it to going from a to b, and then from c to d of g of x, h of y, and then dy dx. Now, the function g of x has nothing to do with y's. There's no y's in it at all. So we can take it out of that integral because it's more or less a coefficient in that for that integral. Okay, now if we consider this thing. So we have a function with respect to y. Once we integrate it, we're just going to get some number. So this whole thing is going to be some specific number. Think of it as 3, for instance. So if we had 3 here instead of the blue, we could take it out of that integral, that a to b integral. And that's exactly what we're going to do next. And then all we have left inside the integral is that function g of x, and we still have to integrate it with respect to x. Okay, but this is the special property that I wanted to state. And that was the reasoning of it. So if you're integrating, and you can split up your functions, then you can just go and integrate the function with respect to x, and then multiply that by the function with respect to y. All right, maybe we'll slip in a quick example here. So let's let r equal from 0 to pi. Let's do pi over 2 cross 0 to pi over 2. Remember, this is the x values, and these are the y values. All right, we're going to integrate over r of sine x cosine y. We can see that we can separate these. This would be our g of x, and this is our h of y. So they're already slightly separated. So we can go from 0 to pi over 2 of sine x dx, and then multiply that by the integral of 0 to pi of cosine y dy. We go to find the antiderivatives. The antiderivative of sine is negative cosine. We do the fundamental theorem of calculus. Multiply that by the antiderivative of cosine, which is sine, and then it's sine y, and we go from 0 to pi over 2 again. We apply the fundamental theorem of calculus, so we get negative cosine pi over 2 minus negative cosine of 0 times that by sine of pi over 2 minus sine of 0, substitute in, and so we get minus 0 plus 1, and then 0 minus, oh, not 0, 1 minus 0, and so we get 1 times 1, which gives us 1. And there